Hey guys, it's Mrs. Miner, and we are going to start talking about isomers for the next few days. So we've actually talked about isomers before. So isomers come in two branches. We've talked about this branch over here on the left before, structural isomers, which is where you have the same number of carbons, hydrogens, oxygens. You just have different bonding. So you can bond your functional groups in different spots. So this would be like 1 pentanol versus 2 pentanol versus 3 pentanol. They're all going to have the same number of carbons. They all have 5, but the OH is in different spots. You can have a hydrocarbon isomer, which is where you branch them off, but you still have the same number of carbons and hydrogens. And you can have functional group isomers where you still have the same carbons, hydrogens, and oxygens. It's just maybe you have a different group that's represented. So that was day 1 of organic. We're coming over here to do stereoisomers. So stereoisomers is where you have the same bonding. So everything is going to be the same, carbons, hydrogens, oxygens. Everything's going to be in basically the same order, but we're going to end up with different three-dimensional shapes for this. So there's 2 kinds of these: conformational, which we're actually not going to spend a huge amount of time on, but I'm going to show you really quick, and configurational. So this is where we're going to spend most of our time, because configurational isomers have a lot to do with biochemistry, and they have a lot to do with healthcare, and so I'm going to show you some examples of that as we go. Specifically, we're going to do cis, trans, E, and Z today, and we'll do optical next time. So for conformational isomers, in a conformational isomer, it's actually the same molecule. So I'm choosing ethane, for example, just to make things easy, because once you start putting functional groups on there, this actually gets pretty complicated. So the idea is, in a sigma bond, so remember that's a single bond, a straight on across the internuclear axis, I can actually rotate this bond, which means that in three-dimensional space, this ethane doesn't just stay like this. This ethane actually has the ability to move. Well, you could move it so that everything is stacked on top of each other. You could move it so that they're complete opposites, and then you can have pretty much anything in between, and all these different isomers are going to have different names, and that's going to affect the three-dimensional feel or the three-dimensional shape of this molecule, but it's easy to fix. Okay, so the idea that we need to get from conformational isomers is that it is possible to rotate around this sigma bond. That's all we need to know. Other than this gets really complicated really fast, and we are not going there because we have other complicated things to talk about instead. So in my configurational isomers, I'm going to have something that defines the sides of the molecule. Most of the time this will be a double or triple bond, but it can also be a ring structure, and you'll see that in your notes. I'm not going to go into it because I don't have enough carbons to build them, but here we go. So in my double bond, I cannot twist this and rotate it like I could with this conformational isomer, which means that these groups are stuck in place. So I chose 2 oxygens here, and so these 2 oxygens are on the same side of the double bond. When they are on the same side of the double bond, we call them cis to each other. If they were to be on opposite sides of the double bond, like this guy here, this is trans. So cis is same, trans is opposite, but this only works when the groups are the same. So why do cis and trans matter? Cis and trans matter for a couple of reasons. One is polarity, which is how we can tell them apart. So in a cis, all of my polarity is going towards the top of the molecule. In a trans, the polarity is going in opposite directions, which makes the overall molecule nonpolar. So what that means is these guys are going to have different boiling points, which means if I happen to accidentally make a mixture of these in the lab, I can separate them by boiling them. Now, other reasons. Remember I said that these configurational isomers have a lot to do with biochemistry? There is an anti-cancer drug called cisplatin. And so in cisplatin will actually bond with your DNA. So these little groups will pop off, so to speak. This is a really simplification of a really complicated process. And they will bind here. And so now when my DNA goes to replicate, I can't, because I'm stuck in place. And that's going to kill those cancer cells. Okay? If I were to try to do this with the trans version, I can't, because I can only bond in one spot. This hydrogen isn't going to do anything. So that's why cis and trans is really important, okay? So over here, what if they're different groups? So I can have different groups that are bonded to my molecule. And how do I tell if they are on the same side or opposite sides? So I have my double bond here, so I can't rotate anything. So when the group differs, I am going to use what are called the rules of priority. So I'm going to divide this molecule in half across the double bond, okay? I am going to look at these guys on the left, and then I'm going to look at these guys on the right. The left is going to get a group of priority. The right is going to get a group of priority. Once I figure out who my groups of priority are, if they're on the same side, then it's Z, and if they're on opposite sides, then it's E. So over here I have a hydrogen and I have an oxygen. So this is going to go by group 1 or rule 1. The higher atomic number has priority. Hydrogen has atomic number 1, oxygen has atomic number of 8. So this is my group of priority, my oxygen. On this other side, I just put a carbon here to represent a carbon. I can put other groups on here later, but we'll get that. So hydrogen is a 1, carbon is a 6. This is my group of priority. So group of priority, they are on the same side of the double bond. This represents a Z, okay? Likewise, I could have them as E's on opposite sides. Okay, well, what if I don't do these guys as, or what if I have 2 of the same atom? I think that's what I'm trying to say. I'm trying to manipulate my stuff and talk to you at the same time. It's not easy. You've seen me do it in class. So what I did is I went ahead and I put on an ethane down here. So we're still going to do our rules of priority over here. The oxygen still has priority over the hydrogen. But over here I'm going to have to go to rule 2 because both of these are carbons. So then the longer carbon chain becomes the group of priority. So this one has 2 carbons versus this one just having 1. So this, they're both on the same side, my groups of priority, would still be a Z. So hopefully this helps out. If you want to see some pictures of how to do this with ring structures, those are in your notes. In the meantime, I really honestly hope I get to see you guys at some point.